Alright, so we're going to start off the last unit in the course, and we're going to look at something called binomial expansion. We've actually done some kind of binomial expansion back in grade 10 when we took a binomial, let's say 2x plus 3, and we expanded it out. Let's say it was 2x plus 3 all squared. We'd expand that out doing 2x plus 3 times 2x plus 3, and then expand and simplify that using an array. So this is the basis of what we're going to be working with today, is that kind of work. Before we get into it, what you see in front of you is a triangle. It's a special triangle called Pascal's triangle, and it's actually going to be used a lot. If you ever go into data management, you're going to see a lot of this triangle. But for now, when you take a look at it, I want you to try and see how we generate each row. Okay, so we start off with a 1, and then 2 1s, and 1 2 1, then 1 3 3 1, and so on and so forth. I want you to try and figure out how we generate each of the values in the following row. And once you can figure out the pattern, I want you to try and complete the next 3 rows of the triangle. Okay, so take a minute, try and figure out the pattern, and see if you can figure out what goes in the last 3 rows. Okay, so hopefully what we've seen is that, well, for starters, as in terms of pattern, we have 1s along all the diagonals. And from there, how we get the other values in the next row is by adding the 2 numbers to the top upper left and upper right of it. So for example, going from, let's say, this row down to this row, we have over here, if we have 1 plus 3, so we have 1 and 3, we add those together to give us 4. We do 3 and 3, add those together to give us 6, and then again over here. So here, for the following row, we have 1 plus 4 to give us 5, 4 plus 6 gives us 10, 6 plus 4 gives us 10, 4 plus 1 gives us 10, and so on and so forth. So then we can create the next row. 1 plus 5 gives me 6, 5 plus 10 gives me 15, 10 plus 10 gives me 20, and so on and so forth. So if I follow that pattern, I can quickly generate the rest of these rows. And in theory, this triangle could go on forever. Okay, this seems like a reasonable place to stop, but again, in theory, it's an infinite triangle. Okay, so this has some special uses. Again, lots of uses in data management. We're going to hopefully see a pattern with that in what we're doing coming up. But first what I'd like you to do is, in a group or on your own, be a lot faster in a group. You can divide and conquer the work. I want you to expand and simplify each of the following expressions using arrays. Okay? Okay, so I'll get you started on this. So if I want you to do a plus b all squared, this is the same thing as a plus b times a plus b. So if you use an array, you can expand everything out. So a times a is a squared, a times b is ab. We have b times a, that's another ab, and here we have b squared. So that particular one gives us a squared plus 2ab plus b squared. Okay, you're going to do the exact same process for a plus b all cubed. And you have a couple of options. You can write this out as a plus b times a plus b times a plus b, and then just take turns multiplying. You can multiply the first a plus b pair of a plus b's together, and then multiply that one by a plus b. Or, if you're smart and you want to save yourself some time, you can rewrite this guy as a plus b all squared times a plus b. And since we already have the previous one, a plus b all squared, we can set up an array that way. So this would be a squared plus 2ab plus b squared. Okay, so that's 3 columns for the array. And that's going to be multiplied by a plus b. Okay, so I'll let you try that right in your answer. When you're finished that, you can do a similar process to get a plus b to the exponent 4. Okay, so when you're ready to see the answers, push play. But this will probably take you a couple minutes, whether it's on your own or in a group. Okay, so you fill in your array. The trickiest part here is making sure you don't make a mistake with your exponents here. So we get a cubed. Remember, you have a times 2ab, that's 2a squared b, ab squared, a squared b, 2ab squared b cubed. And again, watching your like terms when you put them together, make sure that if you're going to combine them, they have the same exponents in each of the variables. So you wind up, when you simplify, getting a cubed plus 3a squared b plus 3ab squared plus b cubed. If you do something similar and take this expression, multiply it by a plus b again, you get a plus b to the exponent 4, and you get this guy. So what I want you to take a look at here, so we have answers to these three problems. Okay, a plus b squared, a plus b cubed, and a plus b to the exponent of 4. Okay, what I want you to look for now is any patterns or connections you might see between the answers above and the numbers we just saw in Pascal's triangle over here. Okay, so we have a lot of different values you can look at here. Again, try and compare them, see if you can see any patterns. And then once you finish that, once you finish finding those patterns, I want you to try and expand a plus b to the exponent 8 without it using any arrays. Because you can imagine doing this by hand would take you a very, very long time. Try and see if you can use the patterns you see from Pascal's triangle to expand a plus b to the exponent 8. Okay, so what you hopefully noticed here, if you look at the coefficients, I know you have a's and b's all over the place here. If you look at the coefficients here, for this first one you have a coefficient of 1, followed by a coefficient of 2, followed by another coefficient of 1. So our coefficients are 1, 2, and 1. For a plus b cubed, our coefficients were 1, 3, 3, and 1. Then for the last one, 1, 4, 6, 4, 1. If you look at Pascal triangle, 1, 2, 1 is right there in row 3 of the triangle. 1, 3, 3, 1 is there in row 4, and 1, 4, 6, 4, 1 is there in row 5. So the coefficients at least come from the row in Pascal's triangle that is 1 higher than the exponent. So it's a plus b squared, we looked at row 3, a plus b cubed, we look at row 4, exponent 4, row 5. So at least for looking at a plus b to the exponent 8, we know we're going to be looking at the coefficients from row 9. Okay, so let's make a note there. Our coefficients in order are going to be the numbers from row 9. Okay, so if I go back to this triangle right here, I have 1, 2, 3, 4, 5, 6 rows. So row 7 or 8, row 9 is down here. Okay, the nice thing about Pascal's triangle is because the patterns make sense, it doesn't take actually, as long as the triangle is, it doesn't take too long to generate it. So row 9 would be somewhere, somewhere would be exactly down here. So at least those will be our coefficients. Okay, what else do you notice? Well, hopefully we notice that there is, if you look at the number of terms in total here, we have 1, 2, 3, 4, 5 terms for a plus b to the 4th. So we always have one more term than we do exponent, which makes sense because if we need to have all the coefficients from row 5, for example, we need to have 5 terms. So a plus b to the 8 will have 9 terms, which makes sense because we have 9 coefficients from row 9. The other thing you might notice here is that for the a, we start off with the highest power, then the power of a just descends by 1 until it disappears. So looking at a plus b to the power 4, our first term has a to the exponent of 4, next one is a cubed, then a squared, then just a, and then a to the 0, which is 1, so it's gone. And for the b's, it's the exact opposite. So it starts off not having a b, and then it starts gaining a power. So then b squared, then b cubed, then b to the 4th. And the other thing you'll then notice here, if you look at the sum of the exponents and all the variables for each term, it should be equal to the original exponent. So, for example, looking in here, we have exponent 4, exponent 3 with exponent 1 to give us 4 in total, 2 and 2 give us 4, 1 and 3 give us 4, and 4 gives us 4. So you see all those different possible patterns that you see going on. So try and put all that, if you haven't seen those connections yet, try and put all that together, try and create a plus b to the exponent 8, the expanded form. So again, take your coefficients from row 9 of Pascal's triangle and the other things we sort of saw up here and try and create the expansion. We'll summarize all the rules and connections we saw in their next slide, so you'll have them in your notes. But again, first try to do the expansion here. Okay, so your expanded form should look something like this. So I took these coefficients directly from row 9 of Pascal's triangle. So you can see the coefficients were 1, 8, 28, 56, 70, 56, 28, 8, then 1. I started off with a to the exponent 8 for the first term, then took 1 away from the power each time until we ran out. I started with b to the 0, so it was gone, then added a b to each term until I ran out. So, until I got up to b to the exponent 8. So this is a nice quick way you can expand all these out now without actually having to go through arrays. Because you can imagine if you had to do a plus b to the exponent 12 or 13 or 14, that would be a lot of work algebraically. So now creating the triangle takes a little bit of time, but once we have those coefficients, we can follow the pattern the rest of the way to get our final answer. Okay, so now let's actually try to apply that to a few more examples that we can expand. But now let's first summarize the patterns as well. So just to, again, we already talked about this on the earlier slide, just so you have it down in your notes. The coefficients of each term in the expansion are the same values you see in Pascal's triangle. Okay, and more specifically, we talked about which row you want to look at. So two ways you can look at it. So it says here, choose the row where the first number, which is not 1, matches the original exponent. Meaning if you go back here, let's say you were looking for something that was exponent 5, well, you'd be looking at this row down here because the first non-1 digit is a 5. What you may find easy to remember is the way we talked about in the previous slide, where since there's one more term in the expansion, so if something to the power 5, then there's going to be 6 terms. We make sure we add 1 to that number to make sure we go to the 6th row. Okay, so again, whatever you want to remember it is fine by me, but as long as you remember it. So the other rules there's always one more term in the expansion than the original exponent. So if you have a binomial, it's going to be a trinomial. If you have the expansion of something, the exponent n is going to have n plus 1 terms. So again, that again will tell you what row to use. If, for example, the exponent was 8, you would use row 9 for the coefficients. Okay, if the exponent was 12, you'd use row 13, and so on and so forth. Okay, because the number of terms matches the number of coefficients in that row. Okay, and last but not least, the sum of the exponents in each term is always the same as the original exponent. So let's take an example, an extreme example, sum of the exponent 35. Each of the terms would have exponents adding to 35. Okay, and we saw that here with this long expanded one here. Every single term, if you look at all the exponents, 7 and 1 gives us 8, 6 and 2 gives us 8, 5 and 3 gives us 8, and so on and so forth. The sum of the exponents in each term should equal the original exponent. Okay, so that's all, putting all that together. Again, patterns that you see that help us expand things a little bit faster. So let's try and put it to use. So let's try and expand x plus 2 to the exponent 6 without having to do it the long way. Okay, so you want to take a look at Pascal's triangle here again, because that'll help us get the coefficients. So remember, if we want x plus 2 to the exponent 6, that means our coefficients are going to come from row 7. Okay, so you may find it helpful to write out those coefficients down so you have them handy as you're expanding. So there they are. 1, 6, 15, 20, 15, 6, and 1 will be your coefficients. And then from there, we can start creating the expansion. So let's take a look at how that's going to work. So for my first term, start with the coefficient. First coefficient's 1. So I'll write it in there, even though when I simplify it later it's going to disappear because you're multiplying by 1, but just so you see where everything comes from. Coefficient of 1. Then I take the first part of my equation, so first part of my binomial, which is x in this case. So it's going to be x to the exponent 6. Okay, now in theory, the second term of my binomial is 2. Technically I have now 2 to the exponent 0. Now I know 2 to the 0 equals 1, but I'm just showing the pattern here that you're going to see when you're going to expand this out, because you'll see for each term I'm going to subtract 1 from the exponent on x, and I'm going to add 1 to the exponent on 2. Okay, so again, took my coefficient, took my first term to the exponent 6, my second term to the exponent 0. Now I'll do my next term. So my next coefficient is 6. So once I have 6, I'm going to take x, subtract 1 from the exponent, x to the 5. Then I'm going to multiply that by my second term, which is 2, and add 1 to the exponent, so now it's 2 to the 1. Okay, and you continue following the same pattern. So next coefficient is 15. So I get 15 x to the 4. And then it's going to be 2 squared. And I'm going to ask you now to finish off the last 4 terms. So keep following the pattern now and see if you can get it to work. And push play on your edge to see this line. Don't simplify yet, just finish off the rest of the terms, and we'll see where it takes us from there. Okay, so just finishing the pattern here, my next coefficient was 20. Subtracted 1 from the exponent, so it was x cubed. Added 1 to the exponent of 2, so it was 2 cubed. Then I got 15x squared 2 to the 4th, plus 6x times 2 to the 5th, plus 1 times x to the 0, which is also 1, 2 to the 6th. So we're just going to simplify this in part 2 of the video.